Eğer beklemede olan arkadaşımız yoksa müsaadenizle başlıyoruz. Sayımız da artıyor. Evet, herkese günaydınlar arkadaşlar. Hepinizi saygıyla selamlıyorum. Bugünkü webinarımızın konusunu biliyorsunuz. Klima santrallerinde fan uygulamalarından bahsedeceğiz. Burada ben ekranımı sizinle paylaşmak istiyorum. Evet. Herhalde ekranım var. Melek Hanım, ekranım var mı?
Gayet net, evet.
Güzel. Teşekkürler. Şimdi ben başlamadan önce bizde bu webinarın organizasyonunda bize desteği olan İSKİ Yönetim Kurulu Başkanımız Ozan Bey'e sözü vermek istiyorum. Kendisi bir 5-10 dakikalık bir konuşması olacak. Ondan sonra ben sözü alacağım kendisinden. Biraz komisyonumuzdan bahsedeceğiz. Niye bu organizasyonu yaptık? Ondan bahsedeceğiz. Ondan sonra ilk oturumumuza, ilk konuşmacımızla başlıyor olacağız. Başkanım, eğer duyuyorsanız beni, söz sizde.
Teşekkür ederim Aral Bey. Öncelikle herkese hoş geldiniz demek istiyorum. İSKİ olarak pandemi sürecinde, aslında pandemi sürecinden önce planladığımız bir sürü aktivitemiz vardı. Biliyorsunuz ilk yola çıkarken, daha doğrusu bu dönemde yola çıkarken dedik ki üreticilerimizi geleceğe hazırlamamız lazım. Dünyada birçok değişim oluyor. Bizim konularımızla ilgili özellikle bu iklim değişikliği kaynaklı onun temelinde. İşte gazlarla, solucan akışkanlarla ilgili değişiklikler oluyor. ERP regülasyonlarıyla ilgili ülkemizde de hakeza değişiklikler oluyor. Bu CE etiketlemesiyle ilgili değişiklikler oluyor. Enerji verimliliği çok önemli hale geliyor. Dolayısıyla bizim üyelerimizi de bunlara hazırlamamız lazım diye yola çıktık. Tam böyle seminerlerimizi organize ettik. Güzel gidiyorduk senenin başında. Pandemi süreci devreye girdi. Böyle biraz bir bocalama süreci yaşadık. Hani ne yaparız, planlarımızı program. Bu teknoloji bir hazırlık döneminden sonra da bu dönemde özellikle itibaren yoğun bir şekilde planladığımız aktivitelerimizi hayata geçirmeye başladık. Bunlardan en önemsediklerimizden bir tanesi de enerji verimliliği. Enerji verimliliğinin kaynağı bizim ürünlerimizin neredeyse tamamında kullanılan fanların çektiği enerji verimliliği, fanların çektiği enerji, fanların tükettikleri enerji konusu. Bu konuda da tabii ki çok detay, çok teknik bir bilgi. Çok değerli iki tane konuğumuzu Ürün aile komisyonumuz irtibata geçti. Güzel bir organizasyon yaptı. Aral Bey'in başkanlığında güzel bir hazırlık yapıldı. Umarım bugünkü webinarımızda faydalı olur. Çok anlamlı sayıda katılımcı şu anda bizleri. Güzel bir umarım şu anda bizleri izliyor. Çoğu da teknik insanlar, bu konuda faaliyet gösteren, çalışan insanlar. Umarım yeni bir kapı açarız, yeni bir ufuk açarız sizler için. Faydalı bir seminer olmasını, başarılı geçmesini diliyorum. Sözü tekrar bir bırakıyorum.
Başkanım, çok teşekkürler. Evet, ben tekrar ekranımı paylaşacağım. Evet, bu arada yüksek oranda katılımımız var. Çok teşekkür ederiz. İnşallah faydalı olur diye düşünüyoruz. Biz nereden bu konuya değinmek istedik? Belki biliyorsunuz, Eurovent'te farklı ürün grupları mevcuttur. Bu derneğimizle alakalı ve sektörümüzle alakalı. Biz komisyon olarak şu an aktif olarak klima santrali çalışma grubumuz aktif, ama arzu ederiz ki diğer komisyonlar da aktif olsun. Yapımızda iyileştirme yaparak daha güçlü ve daha kapsamlı bir şekilde faaliyetlerimizi sürdürelim istiyoruz. Biz Klima Santrali'nde son 2 yılda baktığımızda biliyorsunuz sertifikalı olan klima santrallerin real unit testleri oluyor. Bu testlerde baktık ki ikinci sırada failure oranına sahip olan fanlarımız var. Klima santrali içerisinde kullanılan fanlarımız var. Bunların da biliyorsunuz yoğunluk olarak santrifüj fanlar, ön eğik, geri eğik ve plug fanlar. Bununla alakalı hem Avrupa'da hem biz komisyon olarak bir takım çalışmalara başladık. Ve dünyada bu konuda çok profesyonel ve deneyimli olan insanlardan destek almak istedik. Şimdi başta MK Derneği ile irtibata geçtik. Onlar da sağ olsunlar destek verdiler bize. Sonra bu konuda EBMPAPST firmasında yıllardır tecrübeye sahip olan ürün yönetim direktörü ile irtibat kurabildik. Onlar da destek olacaklarını söylediler ve bu webinarı organize ettik. Bu arada da komisyonda tüm arkadaşlarıma da teşekkür ederim. Bayağı emekleri oldu. İskit'te de Kaan Bey, Melek Hanım'a da teşekkür ederim. Bayağı emek sarf ettik. Burada benim ekranım donmuş herhalde. Evet, geri gideceğim. Evet, biz komisyon olarak ne yapıyoruz? İskit Eurovent AHU grubunda aslında biz faaliyetimiz var. Daha diğer grupları da yapmaya çalışıyoruz. 2018 yılında kurulduk. Yeni kurulan bir komisyonuz. Üye sayımız gittikçe artıyor, aktivitelerimiz artıyor. Önümüzdeki yılda da bu yılda olduğu gibi etkinliklerimiz olacak. Firma gezilerimiz, tedarikçilerimizi, teknik gezilerimizi ayarlayacağız. Burada da eğer siz katılımcılar, üretici olarak bizimle bu konuda el ele verip daha güçlü olmamızı istiyorsanız lütfen bize katılın. Kapımız açık. Beraber güzel konularımız var. Beraber çalışabiliriz diye düşünüyorum. Şu anki komitedeki üyelerimiz bu slaytta görebilirsiniz. Yaklaşık 15'e yakın firmamız var. Bunun da sayısının artmasını arzu ediyoruz. Desteklerinizi bekliyoruz. Vizyon olarak uluslararası iklimlendirme platformunda söz sahibi olmak istiyoruz. İklimlendirme alanında oluşturacak standartlara müdahale etmek, hatta bu standartların gelişiminde katkıda bulunmak istiyoruz. Yani şu an belki ilk yılımız biraz güncel konuları takip etmekle geçti ve geçiyor ama önümüzdeki 2 yıldan itibaren kendimiz söz sahibi olmak istiyoruz. Takipçiden innovator'a seviyesine geçmek istiyoruz. Bu konuda da güzel çalışmalarımız var. Eurovent'te bir takım komisyonlar var, ürün grupları var. Bu ürün gruplarının içerisinde biz şu an Air Handling Unit kısmını takip ediyoruz ama burada ben listeye getirdim. 12 tane ürün grubu var. Sonuncu da yeni kuruldu. Burada siz değerli profesyonellerin katılımları çok önemli. Ülkemiz adına, sektörümüz adına çok önemli. Diğer ürün gruplarına da katılım sağlayarak aslında bizi de daha güçlü hale getirebilirsiniz. Buradan da geçen başkanımızdan da onay aldık. Buradan herkese seslenmek istiyorum. Eğer diğer ürün grupları konusunda faaliyet etmek istiyorsunuz, bana veya Melek Hanım'a veya Kaan Bey'e bilgi vererek yeterli sayıya ulaştığımız andan itibaren hemen o alanla alakalı çalışma grubumuzu kurup bu şekilde faaliyete resmi olarak başlayabiliriz, konuları takip edebiliriz. Yalnız bunun için o toplantılara katılabilmek için geçen yıl membership structure'ı değiştirdi Eurovent ve hale getirdi, ücretli hale getirdi. Ve bu da ciroya bağlı olarak bir ücretler alınıyor. Ama bizim zaten İskit'imiz Eurovent'in direkt associate member olduğu için direkt kendisi de bu toplantılara katılıp ve oy hakkına sahiptir. Bizler de üretici olarak eğer İskit üyesiysek bu ücretlerde bayağı indirim yapılıyor. Fiyatlar neredeyse yarıya düşüyor. Yani İskit üyesi olarak bu ürün gruplarına daha düşük ücretlerle katılmamız mümkün. Yıllık olarak çok büyük olmayan bir ücret alınıyor ciro bazlı. Ve burada artık oy hakkına sahip oluyoruz. Ben şimdi ilk oturumumuzu SIGLOCH Bey ile başlamak istiyorum. Kendisi EBMPAPST firmasında ürün yönetim direktörü. Yaklaşık uzun yıllar bu konuda çalışmış. Ben bir kısa özgeçmişini sizinle paylaşmak istiyorum. SIGLOCH is Director of the Product Management for Fans at EBMPAPST, Germany. He has spent more than 30 years of his career in fan technology and marketing with 3 well-known fan manufacturers, including EBMPAPST. Together with his team, he is intensively involved in designing new energy-saving and quiet fan solutions and closely follows the global regulation of the fan efficiencies. Interpolation based on the measured fan performance maps. He holds a degree in mechanical engineering from Heilbronn University of Applied Science, Germany, and an MBA from the University of Kentucky. Evet, arkadaşlar yalnız bir konuda uyarmak istiyorum. Sunumumuz bittikten sonra 15 dakikalık soru cevabımız olacak. Ancak soru cevapları chat kısmından bize iletebilirsiniz. Tercihen İngilizce olursa tercümede yanlış olmasın veya teknik terimleri yanlış kullanmayalım diye İngilizce göndermenizde fayda var. Ancak Türkçe olarak gönderirseniz de biz bizim dilimizin el verdiği kadar İngilizceye çevirip sorularımızı soracağız. Katılımlarınız için teşekkür ederim. Umarım faydalı olur. Bundan sonra artık sunumumuz İngilizce olacak. Mr. Uwe, do you hear me?
Yes, I can hear you.
Yes, the floor is yours. I stop my share and give the floor to you. Thank you very much.
Thank you very much for the introduction. And I try to share my screen. 1 second. So there should be the full screen.
Yes, we see.
Thank you very much for the warm welcome. Thank you that so many people are joining my presentation. So today I want to introduce you a little bit the world of fans and the topics behind fans and curves and the usage of fans in applications, especially in air handling units. So fan types is one part of the presentation, and then I will switch over to system effects when fans installed in AHUs. There are some things to consider. I will also talk about fan part load behavior, because nowadays most of the fans are not operated always at full speed, full load. And there's also some aspects about fan efficiency metrics. There are different metrics around in Europe and over the world. And also I will give you some hints about regulations and responsibilities in respect to CE marking and fan usage. Fans for fan types, so fan history. This is just giving an overview about how the things developed in the past. So to have a certain airflow, this is 3 meters per second at 1000 pascals. In the past, you needed about, let's say, 7.5 kilowatts to move this amount of air. And over the time, the things developed from bell-driven blowers, and later on in, let's say, in the 90s, due to the fact that speed controls got more affordable, backward curve, direct drive fans have been introduced in the market, and there was some kind of competition in the 90s when all the telecom companies started to build up their network, and then there was especially in Germany, a project running how to create the most efficient air handling unit, and the fan inside was an EC, or a permanent magnet motor driven fan with backward curved impellers. And now over the time we are at about 4.4 kilowatt to transport this amount of air, and we are moving, let's say, towards 4 kilowatt, which is about 75% of efficiency. Fan categories, they are, as you know, centrifugal fans for lower speed, higher speed, and there are axial fans. And in most cases, nowadays, centrifugal fans are used. Axial fans tend to be more on the low pressure side, but there are also some companies coming up presenting axial flow fans in air handling units. So the characteristics of a centrifugal in general is, as mentioned, a little bit towards higher pressure, and the axial fan to the lower pressure. This is the overall, let's say, explanation of such kind of fans. But there are also, when looking to the theory, which is going back to the Cordier diagram, you see that a backward curved impeller, which is very thin, has a certain pressure development, but the efficiency is low. And on the other hand, on the other side, you have a low pressure axial fan with a small ratio between hub and diameter. It's also lower efficiency. This is the efficiency line over the fan families. And you see the most efficient fan category is a certain dimension of centrifugal, backward curve. And there's also the possibility to create a very special axial fan that could be on the same level. So fan is, let's say, the machine that consumes the most, beside a compressor, the most energy in an air handling unit device. There's always the amount of air is more or less fixed. And what the fan manufacturer tries is to create an efficient fluidic flow machine, which is the impeller, an efficient motor, and an efficient drive. So this is the fan system efficiency. So it's always the target to have the lowest power input to do a certain job. And there are differences when looking into the definition of efficiency. So here on the top, you can see the fan curve. It's the same fan, but one refers to the static pressure, which is this curve, the dotted line. And this curve refers to the fan total pressure. And this has also an effect on the efficiency. So the total efficiency, this is the static efficiency. The total efficiency is always higher than the static efficiency. So this is also explained with that formula. The total pressure is the static plus the dynamic, the flow pressure. And only the fan static pressure contributes to the, let's say, to the job, which is to overcome the losses, the resistances in an air handling unit, the internal losses or the external losses, which are created by the duct system, bends, and all these parts. So it's always, if you compare a fan, the fan effectiveness, you have to bring the data on the same level. So in some documentation, you see the total efficiency. In some documentations, you see the static efficiency. So That's the point here, to make the data comparable. Here we tested an axial fan, which is a very efficient one in this case. It has a static efficiency of slightly above 60% with diffuser and without diffuser. Diffuser regains a certain amount of the dynamic energy. So, but you cannot tell which is the best fan without knowing how the installation is done. That is, I will come to that a little bit later when it's time to talk about system effect. But you also, axial fans, for example, they have a certain area which is dangerous for the installation. They have a stall area which is quite close to the maximum efficiency. So this is there are some risks in that, because stall creates pressure shocks in the air handling unit, and this may cause mechanical damage and vibrations. So wire-to-air efficiency versus component efficiency. Wire-to-air efficiency means that the overall fan is tested, including all the necessary components such as drive, motor, if there's a transmission, and the fan itself. And this ends in the air performance, which is the product of flow and pressure. Here again, total or static. So in the standard ISO 12759, it's mentioned that it's the most efficient way to express wire-to-air efficiency is by measurement, by direct measurement, because there the accuracy is most reliable. Because very often this kind of formula is used. You take the drive efficiency, multiply it with the motor efficiency, multiply it with the transmission efficiency and the fan efficiency. And then people expect to get the fan static or total efficiency. But this is partly true. It's true when the peak efficiency of each component is in one point, but this is not the case. In most cases, you don't fully load the inverter, or you don't fully load the motor, or even the fan is not at its peak efficiency. So that's why there must be a certain factor included that is contributing to these deficits. So as mentioned, you never will see all the components being operated in its own peak efficiency. So DP stands for duty point. So for example, it's just to explain a little bit what I'm saying here, and that's why in the standards, in some of the standards, there's a so-called correction factor used, which is about has the factor 0.9. So when you multiply all the components and then use the factor 0.9, you will get quite close to the fan static efficiency or total efficiency. System effect of fan. So the fan manufacturer can take care about, let's say, the fan system efficiency, but the assembly, it can be expressed also by some kind of efficiency, ETA assembly, I call it here, and this is related to the installation of the fan in the unit. Every fan manufacturer shows in this documentation this kind of efficiency. Some of them only the fan efficiency because they don't add the motor, but at the end it's in almost no documentation you find the installation losses to the system. So this could be, let's say, one effect when you use a plenum fan. If you have a plenum fan, you have filters and dampers in the air handling unit, and if you blow, for example, the air from the plenum directly into a duct system, you will create some losses, and this is expressed by this formula, and it goes in square with the air velocity. And for a sharp edge, there's the zeta factor 0.5. So you multiply this with that, and the higher the airflow in the duct, the higher the losses will be. So this is a part of this a fan manufacturer can never cover in the selection. So you have to be aware of what are the metrics behind. If you use, for example, an axial fan, this might be a good option if you have enough space to use a diffuser, and if you connect it directly to the duct system. If you connect it directly to the duct system, you can make use of the dynamic power of the dynamic pressure. You can regain it and reuse it and create a static pressure out of it by using the diffuser. And so in some application, an axial fan could be a good option, but not in any case. Another point is the interaction of the fan flow and for example, a coil or a filter, which is downstream, which is located downstream of the fan. So the efficiency is not only, or system effect is not only pressure losses due to the flow, it's also the efficiency of the components inside the unit. So if you have a very well distributed airflow through a coil, the coil performance will increase. The exchange rate will increase. So that's why in some cases it's not so good to use a certain fan category like axials, because these fans create a certain unevenly distributed airflow. So you see the velocity vectors of the airstream, and you see the red one is has a quite high speed, and you see here the mixing, the distribution downstream of a centrifugal is better. So if there's a coil downstream of the fan, this coil or filter will have a better effect. So this is another way to express that. And you see here as well on the right, the centrifugal fan, the air velocity through a coil is well distributed. Another way to express that one. In the application, this is another distribution effect when you use a blower. So a blower tends also to have a quite big air velocity in the outlet area, especially on the upper part of the discharge flange. And this you can see also when the air meets the coil. So on the other side, when you have a plenum fan, one or even a fan grid, fan wall, the air distribution over additional components in the unit is better, is more beneficial. So system effect, yes. Overall design and adoption to the air distribution system is crucial for selection. It has an effect on the number of fan and how to position the fan, and also about the fan technology, and for sure about the fan sizes. So it cannot be said that this design or that design is the best one to be used in a air handling unit. It has to be, we have to consider also the circumstances of the usage of the installation if the airflow is going axial in and axial out, or if there's a bend axial in and radial out. Could be, yeah, there are various ways of building AHUs, as you know. So the system effect of the fan installation related to the space around the fan. So I talked about the components, the flow path, and there's also something that is related to the space and how to deal with these losses. So from the fan manufacturer side, I can tell you that things get, let's say, tested. So the correction factors can be created or expressed by certain formulas. So what you need is the space, the width and the height of the unit. And to make it comparable, this could be transferred into the hydraulic diameter. And with hydraulic diameter, it doesn't matter where the fan is located in the unit, and it doesn't also matter if the unit is a rectangular one or as you see here, a square one. And fan manufacturers usually have the possibility to measure this, and this is, for example, the fan, the losses or the fan behavior in a unit, where, for example, the square dimension is about 1.7 times the diameter of the fan. You see, you have no losses. So this is a correction factor is 1. So there are no losses. When the overall dimension, when the area where the air passes gets smaller, let's say down to 1.4 times the diameter, we have about 1.5% of flow reduction. This means to overcome this, you have to increase the speed by 1.5%, and that results in about 4.5% of increased input power. And this is documented in the, this could be documented in the software. And in associations, this is dealt in another way. So, for example, in Germany, there's the you see the source RLT guideline. This is, I would say, similar to the Eurovent guideline. There's a certain guideline to all manufacturers to bring the data, the values, the performance to make it comparable. And first of all, it's necessary to dimension or to define the dimension of the impeller, because the impeller is necessary. Impeller diameter is necessary when judging the effect on the distance to the wall in the unit, and it's also relevant to calculate the dynamic pressure, because the dynamic pressure is related to the section of the fan outlet. So the definition of the diameter is the medium between the maximum diameter and the minimum diameter, because nowadays the impellers tend to get more, have inclined blades, have three-dimensional blades, and therefore it needs a formula to have a common understanding. And also the position of the fan in a unit have to be able to be comparable, and so there's a formula behind that. It's all the dimensions added up and divided by 4. So you have also here an average distance to the wall. And by doing that, there behind these dimensions on the pressure side of the fan, you can calculate then the losses. So if it's above, if A is above 0.6 times the nominal diameter, you should use the factor 10% of the dynamic pressure. If it's below a certain dimension, it's not allowed to be used to be in line with the certification scheme. And this is also done for axial fans. On the flow side dimension, if there's a diffuser, you have a certain loss to be considered. And especially in axial fans, the dynamic pressure is quite high as the flow velocity at the outlet of the axial fan is high. So you see here the factor could have a quite high effect on the performance of the fan. That has to be considered. When it comes to parallel operation of the fans, we have this is also more and more popular to overcome let's say tasks or jobs with let's say high airflow. You know that each fan is adding up the flow. So if you have one fan, you have one flow. If you have 10 fan, you have 10 times the flow. And therefore it needs also some rules. And that's why there are also definitions about how to position the fans inside a unit. It is said it must be horizontal and vertical symmetric design. And then the same formulas than mentioned before occur. And so each fan is considered to be a single fan with a certain space. So how is this in the practical use? So, for example, in our fan software, we tested. We have a certain way of expressing the losses. So you can implement the width and the height of the unit, which results in the different data, average distance, and so on and so on, the diameter of the fan and the nominal diameter, etc. And then these is then calculated. You see here, for example, 10,000 cubic meters against 900 pascals. And just to make it comparable, I put here in the annual 8,760 hours. And this will result in this fan's diameter 500 in energy consumption of 33,066 kilowatt hours over the year. And you see we are quite close to the peak efficiency. And this is how we display that. And as mentioned, the data, the losses can be considered. Like here, it's calculation method for the loss of air power. It's not considered in this value, in this 33,000 kilowatt hours. And I can now, I want you to show how this will happen if we use the RLT way. This is the way I expressed before, or to use the EBMPAPST reduction losses that we found out due to measurements. So as mentioned, here we have the 33,000 hours with no, not considering the losses of the installation in this box. Then we have the association value. So we use the static or the dynamic pressure losses. And here we have 34,200 kilowatt hours. And when we use the real data, if these are, if we use the real data which are tested based on tests, we come down to 33,500 kilowatt hours per year. So if this, let's say, individual method based on tests is certified by the associations, or by the in this case TÜV, then we can use that one, and this helps to, let's say, win the one or the other job, or have a better data that are closer to reality. Coming to another point that is very critical, because it's hard to judge fan part load behavior. There are so many components included in a fan. It's not only the fluidic flow machine, the fan itself. It's as shown before. It's also the drive. It's a motor. It's transmission if there's one, and fan, and the fan itself. So it's very easy to calculate the fan data, and also when reducing the speed, the efficiency doesn't change very much. But this is not the case for the drive. It's not the case for the motor, and also not the case for transmission. The most critical thing is these part load data for components are not available. You see, for example, on the electric motor side, you get at constant speed, you get the part load efficiency. But in fan applications or pump applications, you don't have constant speed when calculating. Usually you have a resistance curve, and along this the motor is operated. But for these data, for this use, you don't find data in the motor suppliers documentation. So here is one solution. It's wire-to-air testing. So, for example, we are testing along the nominal curve, and also in between. I will show this later on as well. Also in between, we have about 10 curves which are tested. And with this information, we can easily monitor what is the behavior in part load. If it's a constant pressure part load, so half the flow coming from 68%, it's down to 52. Even along the resistance curve, where the fan efficiency doesn't change much, you see we come from 68 down to 61, more or less. So, and this is related to the motor and to the drive. Or if you come down, let's say from along the constant volume, it's down from 68 to 54 or something like that. And reliable data in part load can't be calculated because the basis is not there, the data of a different component. So the most efficient and most accurate way is to do some W stands for wire to air efficiency. So as shown before, for a certain duty point, the input power is tested, and with this data, you can be sure to be on the safe side when dimensioning or selecting the fan. It needs reliable data. So for that, it needs also the right test rig. It could be TUV, it could be AMCA, it could be Eurovent, it doesn't matter. So because all these documentation and certification based on the same physics. In most cases, it's the ISO 5801. even the AMCA is based on the ISO 5801. And beside the test rig, it's important also to know about the results of the software. So the software, how close is the software data to the real fan data? And we are in the B0 class for flow, pressure, efficiency, which is quite good. And this has to do with we do a direct testing in this way. So this is, as mentioned before, we do the testing along the nominal curve and also part load curve. These are the gray lines or the blue lines. And along these curves, we measure about 15 points. And the certification scheme for the software selects for each of the fans, which are, all of them are tested, selects randomly duty points. And these are compared, and these are tested then, and these tested data are compared with the calculated data of the software. And this is how we came to these accuracy data here. So the flow plus minus 1% and the power input plus minus 2%. And as you can see here, the installation losses of the fan types are considered as well. So the way to make the fan dimensioning to do it in a proper way, it's best to use tested fan performance data if available. And the selection tool is also one part. Does the selection tool really consider the part load behavior and all the components that makes the fan? So just the fan curve does not really give you a good information. And knowledge about system effect. This is very critical, as you have seen before. We can help, or fan manufacturers can help on the fan side, things that are very close to the fan. So the dimension, the distance to the balls, etc. This we have a certain knowledge. But all the other things that happen in an air handling unit is the position of the discharge dimensioning, etc. This is has to be handled on the AHU manufacturer side. This was a Eurovent fan working group trial to evaluate what are the tolerances of the different components of a fan. That was a task from the Eurovent air handling unit group, and the fan group tried to figure out what is best and worst when testing or having the final system. Final system means drive is included in the fan. So it could be for AC motors between 5 and 24%. The EC calculation, so if it's a PM motor or EC motor used, it's between 3 and 19%. And if the final drive is assembled and calculated by the user, the overall tolerances is between 8 and 50%. So this is really a big difference, and therefore real good data are only wire-to-air data. So coming to that, metrics. I mentioned wire-to-air data. There is also the so-called FEG, Fan Efficiency Grade. This is was developed by AMCA some time ago, but this bases only of the shaft to air. So it's only the fan. It's only the fan without the motor, without the drive, and it compares the peak efficiency of total efficiency related to So here's the peak total efficiency related to the fan diameter. So if you are in the diameter 315, you need an efficiency of 66.5% to be in the FEG 80 class. But this is can be used when considering a fan manufacturer's performance, when the fan manufacturer doesn't offer the motor together with the fan. And how to calculate this is fan total efficiency. As mentioned before, it's the flow multiplied by the overall total, the total pressure divided by the shaft power. So fan total efficiency is used, and therefore FEG omit the power losses associated with the mechanical and electrical drive. Static pressure and total pressure I explained before. It's one thing that has to be considered when comparing the systems. Do we look at static efficiency or total efficiency? At the end, it doesn't really matter, because fan manufacturers don't sell efficiencies. I think they sell the input power at a job that has to be done, and so the best way is to look at the power consumption. This is another metric. This is the EU fan regulation, which is in place since 2011, EU 327, and the metrics uses the wire to air method. So this is called the fan motor efficiency grade. So it's a fan plus motor without the drive, and it looks into the peak efficiency of the fan. So here is the efficiency over the fan input power. And you can see a fan with 10 kilowatt. If it's a backward curve, the efficiency must be 62% static efficiency. This is the limit for 2015. And for 2022-23, because this is under revision, this regulation, it will be 64%. For mixed flow, for axials, the levels are different. So this is closer to reality compared to FEG, because as you see here, the input power is tested versus the output of airflow and pressure. And this mechanism does work against poor fan design. So it's had nothing to do with the installation. It's a pure metric to compare or to take, for example, inefficient machines out of the market. So that was the overall target of the EU Commission when implementing this measure. And you see with a different input rating, the efficiency requirement is changing. Another point is the fan efficiency index. This afternoon you will hear something about AMCA, a fan efficiency index. I don't tell you much about that because you will hear about that. This mechanism does work against poor fan selection. So this is something that is closer to reality. So the fan manufacturer on its side can tell you what the fan consumes under optimum conditions on a test rig, and the fan efficiency index looks into let's say the area where the fan should be operated. So this there you will hear this afternoon about the fan efficiency index, about what is 1, and if it's below 1 it should be used. it's a little bit similar than the efficiency lines that I've shown before. It's also a metric of evaluating the good usage of electrical energy compared to the outcome. So if we compare that, the FEG, the FMEG, and the Fan Efficiency Index, the use is, or what is rated, it's the best efficiency point, and the fan selected duty point. And what result, or what does it help for, is here is evaluated FEG, the fan, the best, or evaluate the bare shaft fan. FMEG looks into the how good is the fan, including the drive, the motor. And the FEI looks into how good is the fan for its application. Coming to another part, fan regulation, and also to responsibility. So I was also involved in the discussion 2008-9 about how to create fan metrics. And the first question what came up was, what is a fan? And this is still not 100% clear, because, for example, today a roof fan is not a fan. A roof fan is a unidirectional ventilation unit. So, but for the time being, a fan consists of at least of a motor, of a rotor, and a stator. And the stator is not a motor stator. The stator is the stationary parts that are around the fan. So it's minimum the air guiding device, which could be a cone. If it's a backward curve, it's the inlet cone. This is the stator. So we have the rotor, the rotational part, and stator is the air guiding part. So who is the one who certifies or issues the certificate of conformity? As you know, CE marking is a self-confirmation method, and that's it. How it works. So the fan, if the fan is supplied by a fan manufacturer and the complete fan, stator, rotor, and motor, then the fan manufacturer puts the CE mark on the fan. If the fan manufacturer offers or sells the incomplete fan, for example this, and does not supply the stator, and if the user of the fan creates the stator, the cone, according to the drawings of the fan manufacturer, then the certificate of the fan manufacturer can be used. But if the fan manufacturer just provides the fan with the motor, and somebody else or the user later on designs an own cone, a different one, different compared to the data, to the one where the fan manufacturer created the data, then the one who added the last part, the stator, to the fan is the one who has to declare conformity. So that means if the fan is not complete and is used by somebody else who is doing who makes it complete, then the one makes it complete gets into the position of being the fan manufacturer and has the responsibility of the declaring conformity. So today in your industry, the air handling unit, there are various regulations in place. One is the regulation for the motor. motor and drive, which is the EU 640/2009, which is now replaced by the new one, 2019-1781. And we have the regulation for fans. This is the one I mentioned before, 327/2011. And the revision, the discussion is ongoing. And we expect in about 2 years that the revision will be in place. And we have the regulation for ventilation unit, which you are aware of, I'm sure. There's also a revision ongoing. And these, so in the, let's say, it can happen that the manufacturer of the air handling unit has to take care about regulation for the motors, for the fan, and for the unit itself. At least the documentation has to be made available. So that was in 45 minutes a trip through the fan industry's topics. And thank you very much for listening. And I'm open now for questions. Thank you.
Thank you, Mr. Ove. It was so nice to listening to you. I enjoyed your presentation. Up to now, we are about 15 minutes in time, and up to now I didn't receive any question, but I have one question for you. And if there is someone have a question, can ask Mr. Ove by writing in the chat segment. There is an application called Fan Standby application in AHUs for the critical applications in the, for example, for operation rooms in the market. And generally, there are two AC fans, plug fans in parallel, and there is an air damper in the let's say, upstream of the fan, and one gravity damper downstream of the fan. But we are not aware of the system effect of this application in the unit. Do you have any experience regarding this application, or have you heard some failures in this type of the application up to now?
No. So you have two fans where the fans go in the same direction, the flow is the same direction?
Yeah.
So you have not parallel operation, you have inline operation of fans?
Yeah, it's inline. There are two fans in the parallel assembly. One of them is working and the other one is in the standby. Now, while the other phase, the other one starts to working by opening the damper and closing the other.
Okay. Yeah. So there's a backdraft, right? Through one fan.
Yeah.
And we also in our software we did testing about what is the backdraft depending on the pressure. So it's related to the pressure. The higher the pressure, the more backdraft you have. And this is also calculated in our software. It's better to avoid it by using a damper. Or is it for emergency use? For emergency?
For the surgery rooms, for the operation rooms, it's popular in hygienic air handling units. Or for the critical application, which it's not wanted to stopping the fan and flow.
Yeah. So the best way to really make it controllable, you need a motorized damper. This is, but this creates also losses. But I think in these applications, you have to live with these, or you do something by hand. So many of the users they create some kind of metal plate and put it when one fan stops and you operate the other one. You just put a plate in the suction area. If that is possible, that is the efficient way, most efficient way, because you have no losses. but it's not really safe, I would say. It's, yeah.
Yeah, correct.
Yeah.
Thank you. And I didn't receive any other question. One question regarding the regulation. What are the issues which are remained in the regulation about the fan? We are aware of the ventilation units, but in the fan regulation, we are not sure which points are remained for solving or for development. Do you have a knowledge about this?
I heard that the draft is close to the final document. It's just a matter of capacity or priority in Brussels. This is what we learned from the commissioner. Yeah. Yeah.
Thank you very much. Eğer başka bir soru yoksa I have received one question. Is your software available for the design engineers?
Yes. Upon request, you can get the software. Yes.
Yeah, you're a representative in the Turkey's Untitled company. If someone wants to have the software, you can ask them. They can supply the software. Thank you. And no question. We are about 15 minutes early.
Sorry for that.
Thank you very much. This means that your presentation was so good. Thank you very much.
Thank you. And you can share the slides if you like. You got my PDF, and you can share with the participants.
Of course, thank you very much. Also, we are recording this webinar. We asked you before. We will share the presentation in the YouTube channel we have for the ISKID. Thank you very much.
You are muted.
Değerli arkadaşlar, şimdi biz birinci bölümü tamamladık. İkinci bölümümüzde, bölümümüzün sonunda bir anketimiz olacak. O ankete katılım sağlayan arkadaşlarımıza PDH sertifikası vereceğiz. O listeye baz alarak sertifikamız olacak. Şimdi bir yemek arası molamız var. Saat 14'te tekrar MK temsilcisiyle başlayacağız çalışmamıza. Direkt Amerika'da maalesef zaman dilimi farkından dolayı bir eğitmen ayarlayamadık ama Orta Doğu'dan bir temsilci firmadan, MK üyesi olan firmadan bir arkadaşımız olacak. Kendisinin sunumunun sonunda da bir anketimiz olacak. O ankete kayıt yaptıran arkadaşlara uluslararası geçerliliği olan akredite bir 2 saat PDH olan, kredisi olan bir sertifika takdim edilecek. Evet, eğer Kaan Bey, Melek Hanım, Başkanım sizin bir katkınız yoksa biz ilk oturumu kapatalım. Ondan sonra ikinci
Aral Bey, bir sorumuz daha var. Şimdi eklediler. İsterseniz bakalım.
Bir soru da
For regulations.
For regulations, if someone who makes less design change is responsible for conformity. Soruyu anlamadım ama Mr. Uwe, there is another question, sorry. For the regulations, if someone who makes less design change is responsible for conformity. Oh, I got the question. You showed in one slide that OEM manufacturers should be responsible for the CE label. I think this question is about that. Can you describe this issue for our audience? Mr. Oba, do you hear me? Your microphone is closed now.
Yep.
Sorry, do you hear me?
Yes.
Yeah, there is a question regarding the regulation and the responsibility of the CE mark. You had a slide regarding this issue, but can you explain this issue a little bit more?
With the CE mark, what specific? Sorry, can you repeat the question?
The question is this: I am reading for regulations. If someone who makes less design change is responsible for the conformity.
Yeah, yeah. So the one, the reason for that is we create a fan, and we make the cone to a certain shape, and we measure the fan together with this cone, and we certify or this fan gets the approval CE marking because of that design. If you change the design, if you make a shorter cone or the tip clearance is different or whatever, it will change the performance of the fan. So that's why you cannot use our conformity certificate of conformity anymore, because the data are changing.
Yeah.
That's the reason. Yeah.
Thank you. So we are going to close our first session. In the second session at 14 o'clock, we will be wait for you. Thank you very much.